Hello everyone, this video is going to cover the lecture notes for week 15. The main topics covered is going to be something called inverse functions and logarithmic functions. All of this is related to the exponential functions we did in week 14. Before we get into inverse functions, let's first review what a function is. We've been using functions the whole semester, but here is a review of what function is. So graphically, if you have a graph, it will be a function. Remember, if it passes the vertical line test. Okay, so this is the vertical line test, which means the vertical lines touch the graph only once, which is the case here. So notice, doesn't matter where you do the graph, it will touch the graph only once. So therefore, this is a function. Okay, again, this is not new. And remember that every function has a domain, which we talk about hundreds of times too, and also a range. So this is what we call a function. Therefore, the next thing is, well, what is a one-to-one function? Now, you cannot have a one-to-one function unless you have a function. So first, you need a function in order to check if it is one-to-one. Now, to be one-to-one, it has to pass also the horizontal line test. And notice that this one doesn't. You do horizontal lines here, this touches the graph twice. So therefore, even though this is a function, this is not a one-to-one function. So therefore, that means that this function doesn't have an inverse. So only functions that are one-to-one will have an inverse, and that's the point of this section. Now, by the way, you can always modify a function to make it one-to-one. Here, if we erase this part and you only define it to go from here to here, then this will be one-to-one, and you will have an inverse. Okay. Now, from section from week 14, so you look to week 14, we saw exponential functions, and the graph for exponential function, remember, was like this, which clearly this one passes the vertical line test, which means it's a function, but it also passes the horizontal line test. So therefore, all exponential functions, exponential, is one-to-one, which means the inverse, this is going to be the symbol for inverse, exists, and I'll show you how to find that. Okay, so that's what one-to-one means. So one-to-one means it has to pass the vertical and horizontal line test. And what's the point of that? Well, that means that you can find the inverse function, which is the goal of this section, one of the goals. All right, so now let's just look to this part in a more formal setting. The domain of a function f is the set of all the inputs of f. A function with domain a is called one-to-one if no two elements of a have the same image. That is, whenever x1 and x2 are different, then f of x1 and f of x2 are different. So this is just a fancy way to say that it has to pass the horizontal line test. Okay, so all of this is a fancy way to say it passes the horizontal line test. Okay, now this is what I mean, but it's different. Let's say that x1 is here, and if x2 is here, you can see that the two values are the same. That's why this is not one-to-one. But here, for every value of x you pick, you're gonna have a different value of y. Now, here is why one-to-one functions are important. The first one is because you cannot find the inverse unless the function is one-to-one. But more importantly is that the domain of one function is the range of the inverse, and the range of the inverse is the domain of the function. So that means finding the domain and range very easily. So for example, you have f and the inverse. The function has to have a domain, it has to have a range, and so that's this one. So the domain of this one is going to be the range of this, and the range of this one is going to be the domain of that one, like you will see on this table right now. In other words, the easiest functions to find the domain and range are functions that are one-to-one. And one-to-one literally means that for every x there is only one y. So for example, here you're given this function using values. So the inverse, you just change the x values with the y value. So it will be 5, 3, 4, 2. It will be -4, -3, -2, and -1. So therefore the domain of f is the range of f inverse, which is what I just told you right now. The range of f is the domain of f inverse. The domain of f inverse is the range of f, and the range of f inverse is the domain of f. Okay. Now to graph the inverse function is actually pretty easy once you have the function. So as long as the function is one-to-one. So for example, let's say that the function is this. Say that this is f of x. Then you're going to rotate about the line y equals to x, which means you're going to replace the x values by the y values. So if you rotate or reflect on the y-axis, the graph is going to look like this now. So it's just a reflection, which technically means you're just switching the x values for the y values. So therefore, the graph of f inverse, which is this one, is obtained from the graph of f by reflecting f around the line y equals to x, which technically all you do is you all the values for x you change it for y, and all the values for y you change it to x. Okay. Now one property or feature that inverse functions have that no other functions have is that to find composition of functions is pretty easy. So to find this, they literally cancel each other out, and the answer is just the input in here, which is 4. That's it. In this case, doesn't matter if the inverse is first and the function second. They cancel each other out, and you just end up with a number in there. For example, let's say that you look into f inverse of -4, which is this value right here, and that's equals to -2. But then you look to f of -2, it gives you 4. So the point is that whenever these are the inverse of each other, there is no need to do any computation. Whatever is in there, that's the answer. So this gives you the following very, very useful function, which says the following. If f inverse is the inverse function of f, then when you do the composition with both of them, doesn't matter which one goes first, this one is always equals to x. So that's actually a big thing, because f composition g is not the same thing as g composition f in general. Not only here they are the same, but the answer is always x. All right, the whole point of look into the inverse first is because when we really want to figure out our logarithmic functions, that's what we're after. And if you remember from week 14, this is what we did, exponential functions. This one passes the vertical and the horizontal line test, so this one is 1 to 1. So therefore this one has an inverse, and the inverse is going to be the logarithmic function, okay? And that's what we're really after in this section. So therefore the inverse function for 10 to the x is called the logarithmic function of base 10. So whatever is the base for the exponent is going to be the same base for the logarithmic function. And the inverse is going to be denoted by log 10 of x. Now by default, you don't write a base, is 10. Now the inverse function of e to the x is well called the logarithmic function of base e, which I told you is the most famous base. And this is denoted by log e of x. I told you that this is the most important base, so it's so important that it even has its own notation. This is usually called the natural log of x. So in general, the inverse function of a is called the logarithmic function of base a, and is denoted by this. This should be a. Now, we did a domain and range for logarithmic functions before. You even have it on the last quiz. So let's review that. So the question says the following. For the exponential function in general, the domain is, and we talk about this, is always everything minus infinity to infinity. And the range was 0 to infinity. This is what you have on the last quiz. Now, since the logarithmic function is the inverse, remember you switch the domains and range. So therefore the domain is from 0 to infinity, which is obvious from here. You can see the red line. And the range is going to be minus infinity to infinity, which again is obvious. This goes from minus infinity to infinity. Now we talk about this multiple times. Anything to the 0 power is equals to 1. So therefore the inverse of that is going to be 0. So log of 1, doesn't matter which base it is always going to be 0. You can see that from the graph. When x is 0, clearly you get 1 in here for the exponential. And when x is 1, you get 0, okay? Because they are the inverse from each other. Now, we did this before, so this is just a review. So let's do that again. It says for the exponential function, which is the blue one, it has a horizontal asymptote of y equals to 0. Why? Because it will not cross y equals to 0. Now, what is the end behavior? Well, y goes to infinity. You can see that as x goes to infinity. So you go to infinity, it will go to infinity. And if you go to minus infinity and the blue line, this will stay in 0. So this will be 0. What about the vertical asymptotes? This has none. Okay. Now let's look to the red line or the logarithmic function. This one has a horizontal asymptote, and the answer is none. The end behavior, this goes to infinity as x goes to infinity. And this one goes to minus infinity as x goes to 0 from the right side. Because you can see this doesn't go to the negative side. And therefore the vertical asymptote is going to be x equals to 0. Therefore you just repeat this in here. This will go to minus infinity as x goes to 0 from the right side. Now, this cancellation property, which we talked about it before, remember when we did this, okay? Remember that F composition F inverse of X is equals to F inverse composition F with X and always equals to X. This property, which is presented for the first time here, is very, very useful when you take higher math classes, like differential equations. By then, most people forget this, and people have a very hard time in that class, not because differential equations is hard, but because they forget this. Remember that what this means is the following, that if you do a to the power log a of x, which is technically this, that the answer is going to be x. Or that if you do log a of a to the x, is also going to be x, which will be this part. The same thing is going to happen here. E to the ln x is going to be x, and ln of e to the x is also just going to be x. And the exact same thing here, 10 to the log base 10 is x, and log base 10 of 10 to the x is also x, which is just this part right here. Now, one of the most useful things for logarithms is to be able to switch from log to exponent or exponent to log. Okay, this is very, very, very useful, and it will make life pretty easy. So what this is saying is that you have log a of x equals to y. Then to change to exponent, so this is logarithmic. So to change to exponential form, you always look for the base first. The base is a. The exponent is going to be y, and then this is equals to x. In other words, when you switch from one to another, the two things that were together, they have to be separate in the other side, but always look for the base first, which is exactly what this is saying. So this is the general formula, which is the one I just did. And these are just special cases where the base is e, and this is where the base is 10. So for example, you have, let's say, log 2 of x equals to 4. The first thing you do is look for the base. The base is 2. So an exponential forms will be 2 to the 4 equals to x. And in this case, the answer will be 16. Or everybody knows that, let's say, 2 to the fifth is 32, right? So which one is the base? Well, the base is clearly 2. So this is the same thing as log 2 of 32 is equals to 5. So this is how easy it is to change from log to exponent, and this is very, very, very important. So here, the base is 5. So it will be 5 to the y is equals to 25. Here the base is e, so this will be log e of 12 equals to x. Remember that you can rewrite this as just ln of 12. Right, before we solve the problems, let's practice more how to change from log to exponent. So let's say this is log and this is exponential. So if you have log x equals to 6, and there is no base, then the base is 10 automatically. So that means in exponential it will be 10 to the 6th power equals to x. Okay? If you have, let's say, log 3 of x equals to minus 1, this means that 3 to the negative 1 is equals to x. Okay, so it's very important to be able to switch from one to another. All right, sometimes you have the exponent and you have to change from the exponent to the log. Let's say you have, for example, 10 to the 3, which is 1000. You always go for the base. The base is 10. So then this will be log 10 of 1000 equals to 3. Okay. So make sure you practice this. So in general, you have, let's say, log of b of t equals to k. That means that b to the k equals to t. Or if you have a to the b equals to c, that means log of a of c equals to b. Okay, so make sure you become very good doing this, and then solving logarithmic equations is going to be pretty simple. For example, let's look to this one right here. The base is 10 since there is no base, so let me rewrite it. This is technically this. Okay, so you change to exponent. In exponential form, it will be 10 squared equals to x plus 1, which means 100 equals to x plus 1, which means x equals to 99. So you can see the key to solve it was to change from log to exponent and solve for x. Now, sometimes the question is given on exponent, and you have to switch it to log to solve it. So here it will switch to log. This will be log e of 0.5 equals to x plus 1. Remember that this, you can just rewrite it as ln of 5. So therefore x is going to be, sorry, ln of 0.5, not 5. So this is 0.5. So therefore x is going to be ln of 0.5 minus 1. Then just use a calculator and you're done. Now the last problem we did in week 14 was related to this. And remember there was a part where it asked you how long will it take to get to 1,000 people. And I told you couldn't solve that without logs. They give you a graph at a point and you get estimated from the graph. But now using logs, you should be able to solve the problem. So this is telling you how long it's going to take to get to 1,000. So 1,000 is going to be equals to 10,000 over 5 plus 1245 e to the minus 0.97 t. Now, if you cross multiply, remember this is a 1 in here. So 1 times 10,000 is going to give you 10,000. And in the other side, you're going to multiply 1,000 times this. And you should definitely check this with a calculator. This is 5,000 plus 1245, then 3 zeros, e to the minus 0.97 t. This simplifies to 10,000 minus 5,000 will give you 5,000. And this is equals to 1245, 000, e to the minus 0.97 t. Okay? Which means that e to the minus 0.97 t is equals to 5,000 divided by this. The zeros can cancel, and this is actually equals to 0.004. You should check on that. All right, so therefore to finish the problem, you're gonna, this is what we have from here. We have e to the minus 0.97 t is equals to 0.004. So you switch from log to exponent. It's going to be log e of 0.004 is equals to minus 0.97 t, which means t is going to be ln of 0.004 divided by minus 0.97, which is 5.69 or around 6 years. Okay. Now, finally, there are three properties or three laws of logarithms that if you're gonna be a Sternmayer, you have to memorize because you're gonna use it over and over. The first one says that if you multiply two logs, then it becomes a sum, that the quotient becomes a subtraction, and that the exponent becomes a multiplication. Okay, this should not be surprising because remember the logs are the inverse of exponents. Remember or recall this, that if you have x to the 4 times x to the a, this is equals to x to the 4 plus a. So when you multiply, you add exponents. So that's where this comes from. If you divide, you subtract. So this is not new. So you should definitely memorize these rules. So now using these rules with switching from exponent to logs, you can solve any problems that you will see right now. But first, let's practice these properties. So according to property number two, so you have a quotient here or you are dividing, so this is going to become a subtraction. Before you do that though, make sure that you rewrite this. Remember that the cube root of c is the same thing as c to the 1/3. We did that before. So therefore, before you do anything, just rewrite it. This is the same thing as log of ab over c to the 1/3. Okay. So we haven't done anything so far. I just rewrote it. Now by property number 2, this will be log of ab minus log of c to the 1/3. Then by property number 1, since this is a product, it's going to become a sum. So this will be log of a plus log of b minus log of c to the 1/3. Now the only one that has an exponent is this one, so this part is done. So you just rewrite it, and then the exponent will go in front by property number 3. So it will be 1/3 log of c. Okay. So the exponent goes in front. All right. So now this one by property number 1, this becomes a sum. So this is log of x plus log of y to the 7. Then by property number 3, since you have a exponent here, that has to go in the front. So this will be log of x plus 7 log of y. Now, if you're able to go from here to here, you should be able to reverse the steps and get to these two. Okay, so practice going backwards too. And this is what I mean before I solve this problem. If you have, let's say, 2 log of x plus 4 log of y, well, if you reverse the steps, that means that this came from log x squared plus log y to the 4. Now, since this is a sum, that means it came from a multiplication. So then this will be log of x squared times y to the 4. So you should check that you can go backwards. Okay. All right, so here, in this case, this will be the same thing as log of x cubed plus log of x plus 1 to the 1/2. Now, since this is a sum, this means it came from a multiplication. So it will be this. And finally, I mean, this is technically done. You get this far, but remember, this is the square root. So unless the question asks, you don't have to write it in square root form, but that's what it is. This is x plus 1. That's it. You should practice doing this, like expand it, and it should end there with this part. All right, let's try the next one. Now this is an equation. Now this is asking you to solve it. So on the left side, you have log of p. Remember, since the base is missing, that means the base is 10. So that's very important. Now on this part, notice that this is a subtraction. So let me do this on this side. You have log of p0 minus c log of t plus 1. This is the same thing as log of p0 over t plus 1 to the c power. Because remember, this is going to be log of t plus 1 to the c. Okay? So therefore, this means this is equals to log of p0 over t plus 1 to the c. Now, if you have log here and log here, there is no need to switch to exponent. Otherwise, you have to solve it. In this case, you can just literally cancel them out. And from here, this means that p is equals to p0 over t plus 1 to the c power. That's it. All right, let's do one more last example that is less abstract than that one. Let's say that the problem is this. It's asking you to solve this. So you have log, now the base is 2 of x plus log 2 of x minus 3, and that this is equals to 2. So this is a sum. That means that it came from a product, so this will be log 2 of x times x minus 3 is equals to 2. Okay? So then you switch to exponent, this is going to be 2 to the second power is equals to x times x minus 3. Or 4 is equals to x squared minus 3x. Alright, so if you set it equals to 0, this is x squared minus 3x minus 4, which you can factor as x minus 4 and x plus 1. So the answer is 4 and negative 1. Remember that the domain for log is only the positive values. So therefore, this one will not be part of the answer. So the only solution will be this, and that's it.